All right, hopefully a relatively short video, just doing a stoichiometry problem. So yeah, let's get going. Let's say I have this reaction, okay, and let's just say I just pick a number here. Let's say I don't know. Let's do maybe a nice clean 150 grams of let's do phosphorus. Why not? Of phosphorus. All right. And basically, what I want to know in this problem, right, is like how many grams of hydrogen would I need to react all of that, and like how many grams of oxygen would I need to react all of that. Basically, like these are ingredients, right? Like in the idea of the baking that we've talked about. If I'm baking a cake and I have 1,000 eggs, the implication is how many cups of flour would I need to bake all 1,000 eggs, right? Like if I just, like that's a lot of eggs, right? If I want to use every last egg to make cakes or whatever I'm making, I would need to know what the ratio is of, flour, cups of flour to eggs, or cups of water to eggs and whatnot. Okay, it's like the parts of the recipe, right? And then, of course, we want to know, well, how much stuff am I going to make, right? And that be this guy right here, the H3PO4. Okay, this would be the synthesis reaction of what's called phosphoric acid, a very strong and very scary acid, made up of these three relatively not dangerous things, although phosphorus is a bit dangerous. But anyway, so first thing you want to do in a stoichiometry problem is one of two things, right? Either we can balance it first, which is perfectly reasonable, nothing wrong with that, or we can do molar masses first, all right? Either way works. Okay, like there's not like a right way, wrong way. It's up to you. So I just balance it. That's balancing to me is kind of the first thing I think of. So for balancing this, let's change colors here for a second. When I have an odd number like 3 here and an even number like 2 here, okay, usually I'm going to start there. It's usually a pretty logical place to start. So for balancing this, we need a common multiple, usually the least common multiple, though not always. And that would be 6. So to get 6 hydrogens, I'll put a 3 here, and to get 6 hydrogens, I'll put a 2 here. Okay, so that's 6 hydrogens, yay. Now I have how many oxygens? 8 over here. So to get 8, I would put a 4 there. Okay, and now I have 2 phosphoruses, and this one's easy. Just put a 2 here to get 2 phosphoruses. Okay, it's pretty easy to balance. Hopefully you agree. And now we can do our molar masses. Again, the molar masses, I could have done them first. It doesn't really make a difference. But for the molar masses, let's see. So H2 is just going to be, and this, again, this video is the simpler version of stoichiometry, right? So I'm only doing to the ones place, the whole number. Okay, so it's a little bit, if you're watching this taking a chem class, you might be like, wait, aren't we supposed to do the decimals? Yeah, this is for more of a freshman level, if that makes sense. So this would be 2 grams per mole. Okay, oops, I don't know what happened there. My pen decided to be crazy. Phosphorus is just 31 grams per mole. Oxygen, O2, just like the H2, 16 times 2 is 32 grams per. Here, let me move this. Can I move myself? There we go, look at that. Grams per mole. And then the H3PO4, the phosphoric acid. So let's see, we have 3 from the hydrogen, we have 31 from the phosphorus, that's 34, right, adding them together, and then 4 times 16 is 64. So 64 plus 34 is what, 98, I believe? Is that right? Let's see, 64 plus 31 is 95, plus 3, 98. Yeah, that sounds right. Okay, awesome. And now you say, what do I do? And this is where I'm a big proponent, a big advocate, an evangelist. Good, nice words there. At least I hope they are. I don't know. Maybe I sound kind of crazy. For the fence method. Okay, and the fence method, we call it this because it looks like a fence, right? Here's your, I guess, your side piece. What do you call that? Your strut. Well, I guess not a strut, 'cause it's not diagonal, but this part of the fence. Then we got our fence post, right? And what is it going to look like? We start out with our grams of phosphorus. That's what I'm given here. Okay, so I'm going to start with that. 150 grams of phosphorus, 150 G phosphorus. Okay, first thing I got to do is I have to get this into moles. I have to convert it to moles. I cannot work with a chemical reaction if it's not in moles. It's got to be moles. So I'm going to use my molar mass of phosphorus. So 1 mole of phosphorus, 1 mole of P per every 31 grams of phosphorus. Okay, that cancels out the grams of phosphorus. That's good. Now we have moles. Now, what you're finding in this problem is everything, right? We're trying to find the grams of hydrogen, the grams of oxygen, and the grams of phosphoric acid. That's 3 answers I'm going to need. It doesn't matter which one I do first. It really makes no difference. Obviously, if you're taking a test or a quiz and it says find this one thing, then I would do that one thing, right? But if it says find everything, well, then, we start wherever we want to start. I'm just going to go left to right. So I need now the ratio of hydrogen to phosphorus, and that is 3 to 2. There are 3 moles of hydrogen per every 2 moles of phosphorus, right? 3 to 2. And again, notice that the fence method is nice because you can cross out stuff. You know it's in the right spot. Okay, you might have said, why isn't it 2 over 3? Well, they wouldn't cancel out. That's the issue. Okay. So we're not done because now we're in moles. Moles is nice, but we like grams because you can measure grams, right? So you use moles to work with the chemical reaction, and then when you have your moles, then you can go back to grams because that's what we like. We can measure grams. So now we need the molar mass of hydrogen, and that is 2 grams of hydrogen per every 1 mole of hydrogen, H2. Okay, H2, and again, that cancels out the moles of H2, and we're left with grams of H2. And that'll be one of our answers. And this is where you want to use your calculator, right? I mean, I guess you could try to do it in your head. You could try to do it on paper. Cool, I guess. I don't know. Just seems a little silly to me, but, use your time how you wish. So 150 divided by 31 times 3 divided by 2 times 2. And I get, I'm going to round to the hundreds place here just to make things a little bit simpler with space. 14.52 grams of hydrogen, H2. Okay, that's one of our answers. Let's get another one. So I'm going to now switch over, and I'm going to do now the oxygen, right? We already have the phosphorus, so now we'll do the oxygen, okay? And it's going to look like deja vu because we're starting out with what we're given, 150 grams of phosphorus. Uh-oh. Well, I'll try to write this. It's got a little slanted. My fence is built a little slanted, I guess. Molar mass, right, of the phosphorus, 31 grams. There we go. I guess we kind of fixed it a little bit. And now the molar ratio, the stoichiometric coefficients, those are the numbers in front. For oxygen, it's going to be 4 moles of oxygen, 4 moles of O2 per every 2 moles of phosphorus. I've had students in the past ask me, can I simplify that to 2 over 1? You could, right? It's not wrong. 4 over 2 is the same thing as 2 over 1. It doesn't really do anything. I mean, I would argue it doesn't really do anything helpful for you. Maybe it makes it a little bit quicker, but it doesn't change the answer, right? Just simplifies it a little bit. So then what I'm going to do is get the molar mass of oxygen. The molar mass of oxygen is 32 grams per mole. 32 grams of O2 per mole. Oops, let's try that again. Mole. Wow, my pen will behave itself. Moles of O2. Okay, and this will give us an answer of, let's see, 150 divided by 31 times 4 divided by 2 times 32. And I get an answer of, big number, 309.68. Again, I'm rounding to the hundreds place in this case, and that's grams of O2. Okay, grams of O2. All right, bigger number. And you might say, is that right? You always check your answer again. There's a great way to check our answer. We'll do it at the very end here. Okay, so now we're on to our last one, which is the phosphoric acid. And again, it's going to be deja vu because we're going to start out with our 150 grams of phosphorus. There's my fence. 1 mole of phosphorus per every 31 grams of phosphorus. Now the ratio is 2 to 2 in this case, which is nice because that's 1 over 1. But again, I'll just for thoroughness write it out. 2 moles of phosphoric acid per every 2 moles of phosphorus. And then lastly, the molar mass. The molar mass of phosphoric acid is approximately 98 grams of phosphoric acid per every mole of phosphoric acid. All right, and we use our calculator. 150 divided by 31 times, so it's 2 over 2, so it's times 1 times 98. And I get 474. So 474 point, and I get it right into the hundreds place, 19 grams of phosphoric acid, H3PO4. Now here's the beautiful thing about this. You can check your answer. So how do you check it? The whole premise of stoichiometry is that mass cannot be created or destroyed, right? The law of conservation of mass basically says in any chemical reaction, when there's a reaction happening, I don't care which one it is, the number of grams on the reactant side has to be the same grams on the product side, because you can't destroy atoms and you can't make atoms. Now, in a nuclear reaction, that's different, okay? Like, we've learned more about the idea that matter and energy are interchangeable, but that doesn't work in a chemical reaction, okay? So in a chemical reaction, this is true. Mass is conserved. If there's 20 grams on the left side, there's got to be 20 grams on the right side, okay? So we can check our answer. How do we do it? Well, we say, hey, I have this many grams of hydrogen. Well, that's this guy right here, right? I have how many grams of phosphorus? Well, that's from the beginning. That's 150, right? That's what I'm starting with. So that would correspond to this. And then I have my grams of oxygen, which is this, right? So I have 3 reactants, and guess what? They're all being added, right? So I can take those grams and add them together. And if I'm right, assuming I did my math right, I should get about 474.19. Now I say about, and you might say, wait a second, you just told me that has to be the same. We've been rounding this whole time, right? We've been rounding to the hundreds place, which means our answer might be off by 0.07. It might be off by 0.1, and that's okay because we rounded. Now, if we're off by 50, if we're off by 7, then we might have a problem. Okay, so let's see. Fingers crossed it'll work. So, calculator, 150 plus 14.52 plus 309.68, and I get 474.2, which is, hopefully you're saying, oh, good, it worked, right? 474.2 is 0.01. That's 1/100 of a gram off from my answer here, okay, which is the phosphoric acid, right? That's the only thing, that's the only product, okay, which means every last gram that was hydrogen, that was phosphorus, that was oxygen is now in these phosphoric acid molecules, which means that they're definitely, that all the mass should be there, if that makes sense. And getting 474.2, that is, I mean, again, ideally it's perfect. Ideally it's 474.19. But again, because we rounded, that's okay. All right. So this is good confirmation that our answer is correct. There is certain situations where you could do this and still get the wrong answer. If you, I don't want to make this too complicated, but basically, if you have the wrong ratios, okay, like if you don't balance it correctly, then you could have the right check but still have the wrong answer, and that's why balancing is so important. Okay, molar masses, they have to be correct, but again, the assumption here is that those are hopefully the easier skills to do. Okay, the stoichiometry, the stuff that you see in the fence, that's the hard part. I put it in quotes because I don't think, if you put it in the fence, I think I would hope you'd say it's not that hard. I'd hope you'd say it's not as bad as it looks. It certainly looks scary, but when you walk through it, you're like, oh, okay, hopefully you're saying that kind of makes sense. Okay, so we'll call it quits there. But yeah, any stoic problem can be approached this way. They can certainly get harder, right? More stuff, throwing in molarity, throwing in pressure of a gas, volume of a gas, trying to find moles of gas. I mean, you could certainly make them harder. But for the fundamental idea of stoichiometry, hopefully this video helps you out a lot and makes you say, hey, that's not as scary as it looks. All right, well, we'll call it quits there. Have a great rest of your day, and good luck.